To investigate other proofs of Sylvester's theorem, we need to look at a very important concept in geometry, which is the point-line duality. The point-line duality, often taught in the following way, where it says the dual of a point AB is a line y equals ax minus b. This is also the way that's taught in the computational geometry course, and some of you might be familiar with it. However, in this course, I would like to put aside this definition and stick with some other definition. I'll need to add that there are many more definitions of duality. While all of them have the same basic properties, such as they turn a point into a line and they preserve incidences and various other properties, the exact definitions can be changed. So the definition I would like to present is the following. Assume you have a point AB, which has distance d from the origin. Connect it to the origin and extend this line up to 1 over d distance from the origin. So this distance would be the inverse of this other distance. Now the dual of point AB is defined to be the line that is perpendicular to this line segment at this point. This definition is a bit more complicated than the previous definition, so I would like to justify why I would like to stick with the following definition. Those of you who have taken the computational geometry course know that in the above definition we have some problems. For example, we cannot represent vertical lines in this formulation, so vertical lines do not receive any dual. But what about the following definition? If you look at the projective plane, and I will use an applet to show this to you. Now let's look at some properties of this duality transformation. I will adopt the following convention. I will call this left window the primal space, and this right window the dual space. Consider a point in the primal space. This will be a line in the dual space. And it has the following properties. If you put any point on the dual line, you'll get a line in the primal space that passes through the point. As you can see, as long as I move this point in the dual space on the line, my line in the primal space will correspond to a line that passes through the point. This of course means that if I put 2 points in the dual space on the line, they correspond to 2 lines that intersect on that point. And of course the same is true for the dual space, for the primal space. Put 2 points on the primal space. They will correspond to 2 lines in the dual space. And that intersection point is a line that passes through them in the primal space. This of course holds with respect to any points and any lines, even the lines at infinity. Place 2 parallel lines in the dual space. To do that, we'll need to have 2 points that when you connect them, the line passes through the origin. What is their intersection point? Their intersection point in the dual space is a point at infinity. How is that represented? It's represented by a line that passes through the origin and connects those 2 points. There are other properties of this duality transformation. Let's fix this point in the primal space. And pay attention to the line segment that connects the origin to that point. Now what happens when I put a point in the dual space that is above this dual line and I move it around? Notice that any of the lines that I get in the primal space do not intersect the line segment to connect the origin to the point. For example, this one, or this one. None of these lines intersect this line segment. To get a line in the primal space that intersects this line segment, I will need to go to this other side of the line. As you can see, all the lines that I create by picking a point in dual space below this dual line will be corresponding to lines that intersect that line segment. And finally, let's look at what happens to Sylvester's problem when we pass it through this duality transformation. If you remember the Sylvester's problem, we had a bunch of points with the assumption that none of them lie on a common line. I would like to show there exists a line that passes through only 2 points. When we look at this problem in the dual space, we will have a bunch of lines. The fact that all of the points in the primal space do not lie on a common line implies that these lines do not pass through one common point. An ordinary line in the primal space corresponds to an ordinary point, and it's a point where only two lines intersect. For example, that is an ordinary point, whereas this one is not an ordinary point because it passes through three points in the primal space. However, these intersection points, they are all ordinary points. And also this one. As you can see, with duality, you can have a very nice representation of Sylvester's problem. It corresponds to finding vertices of degree 4 in an arrangement of lines where not all of them pass through a common point.